Thank you. Yeah, good morning, everyone. Thank you for joining. I'm speaking here on behalf of the Chapter 13 team about the gas and dust dynamics. And since PP6, we have really learned a lot. So starting from the large-scale MHD-driven wind flows, global simulations, until the disk physics, radiation MHD models, and really until the mid-plane layers where you have the dust concentration and the streaming instability. So let's go a step back. So why actually the gas and dust dynamics is so important? It connects to many, many different regimes. So we learned in Shakura and Sunyaev in '73 that the gas turbulence creates the needed stress to transport angular momentum and to drive the gas disk evolution. We also know that the gas turbulence is responsible to create the relative velocities, to control the dust evolution, and eventually also affect the planetesimal formation and evolution. And as we have heard yesterday, it creates structure formation. So very important, the structure formation process. Here I took this slide from what we have seen yesterday already. In this talk, I will focus on the hydrodynamic instabilities, the MHD, and the dust multifluids one. So I will not cover here self-gravity or embedded planets. Okay, let's move on. So I will focus first on the gas part. And here, what we have to understand is, of course, how the mass accretion rate is happening. So in this famous plot here from Lee Hartman, you see on the y-axis log scale of the mass accretion rate over the time. And you see at the beginning, you are dominated by the envelope, by gravity. So gravitational instability is creating these large accretion bursts. And then once you reach the T-Tauri phase, these bursts get less, and you enter this T-Tauri phase. So this is what I will focus in this talk on, where the mass accretion rate is between 10 to the minus 9 and 10 to the minus 7 solar mass per year. And remember, we have seen in the talk from Benoit, in the Chapter 9 talk, which focuses really on this innermost part where you still have the envelope falling in. And we have also learned yesterday from Agnes here, Chapter 10 talk, who focuses on these accretion bursts. And these actually enter also here this zone. So I will not speak about this in this talk. Okay, how do we relate the accretion rate now to the turbulence? As I mentioned, there was this famous Shakura and Sunyaev parameter alpha, which is a stress to pressure ratio. And to explain the typical mass accretion rates, we need an alpha value in the order of around 10 to the minus 2. So in this plot, I summarize what we have learned in the last 10 years. So this is here height in units of h, the pressure scale height, over radius, both in log scale. And you basically see here 2 different or 3 different regimes. So the first important regime is the MHD regime here, which covers the magnetorotational instability here at the midplane layers, MHD-driven winds, and photoevaporation-driven winds. In this middle part, you see the non-ideal MHD regime, or the case where the magnetic fields decouple from the gas. So I will first focus on the MHD part. And for the MHD to work, you need ionization, right? So this summarizes here what we have known today. We have thermal ionization in these hot inner parts, where the alkali metals in the gas phase does the job to provide the free electrons. Then you have the thermoionic emission in the regimes, where you also have dust grains releasing free electrons. But most importantly, you have the X-ray and the FUV in the upper layers. And obviously, the cosmic rays, they do a very special job. So they can, on one hand, penetrate much deeper than the others, but they can also get shielded by the magnetic fields. So we have to be careful. It can be very dynamical. But eventually, you need this ionization for the MHD to operate. Therefore, it's really of a big importance. Okay. So let's start with the MRI. So in PP6, a lot of people have said, well, the MRI is dead. But I want to remind you, the MRI is still important. Not only for the inner parts, where we know that it drives the required accretion of an alpha stress in the order of 10 to the minus 3 to up to unity, depending on the magnetic field strength and also on the magnetic diffusivity. And in the outer parts, the MRI can also get important. So we should not forget the MRI. So I mentioned magnetization. We heard already about that. So these famous plasma beta values, so if the beta value is very high, magnetic fields doesn't play a big role, and if this beta value is smaller than unity, it's really dominated by the magnetic fields, which is in the case here in the upper layers, in the low density regime. So let's look at this movie, which shows you here a 3D radiation MHD simulation. So you see the irradiation layer, turbulent velocities, you see several hundreds of meters per second in the midplane layer, and reaching up to 1,000 meters per second in the heated layers. And you see even current sheets can heat the already irradiated material even more. Okay, let's move on to the thermal winds. So for these thermal magnetohydrodynamical winds, we need a high magnetization, so low plasma beta, to explain the accretion rates we see. But we also have a transition to a pure photoevaporation-driven wind. So in this case, the magnetic field is so weak that you are left with the pressure-driven wind. And also, most of these models predict that this wind mass loss can be quite efficient. So we should keep this in mind. But there will be a chapter today at 2 by Sylvie Capri. So I will focus here. You should take a look at this. And yeah, well, what is really new in this since PP6 is that we have these first global models. So we will hear more about that today. Okay, move on. Let's now talk to this middle part where the non-ideal terms become more important. There's the ohmic diffusivity, Hall diffusivity, and ambipolar diffusion. They all reduce the effect of the magnetic fields. They reduce the effect of the MRI. But you still can find some residual turbulence. So the alpha values are here in the order of 10 to minus 4. So this is here important to notice. What is also important is regimes. So these regimes are prone to magnetic flux concentrations. What does it mean? So it means that you can have strong perturbations, or you can create strong perturbations in the surface density, and in this gap you can have very magnetized regions. So magnetic flux is really concentrating because of the changes in the magnetic resistivity terms. And that's very important. So here's a movie by William Bethune, who shows you this wind-driven layers here in the upper layers, you see in the bottom magnetization. So blue means very magnetized. So you hear the wind layer dominated by the magnetic field. But then you can see that you create structures, and this is exactly due to this magnetic flux concentration. You can see it also here, these blue stripes here in the midplane layer. So very, very important. Okay. So what is now crucial is actually, this is something you should really take home, is we have to understand the magnetic flux transport. So there are now works starting on that. So we have to understand, how the magnetic field is actually advected, the vertical one. We now think that in these parts where the turbulence is very efficient, that the advection is inward, while in the non-ideal dominated regimes, the advection is outward. So why is this so important? So if you remember, the magnetic field strength we predict is around milligauss. But when you remember here in Benoit's talk, so from the collapse simulation, they think that, well, it's around 100 milligauss. So we still have to go down from these 100 milligauss to several milligauss in a couple of 10,000, couple of 100,000 of years. So this is something we really have to understand probably until PP8. Okay, let's move on. So about the heating mechanism, so the MHD part are very efficient in heating, especially in this inner part, the turbulent heating. This becomes relevant, especially if these inner parts become optical thick, then you can have even an enhanced convection, so turbulent convection regime. Not to forget the reconnection layer, as I showed in the movie, and these reconnection layers are particularly strong at the edges of this Dead-Zone regime. And then also what was shown here by some authors, the ambipolar heating. I mean, it is strong, but on the other hand, it is in a regime where the optical thickness becomes small, so in this layer we can actually very efficiently cool. So in the end, the ambipolar heating doesn't change the temperature very much. Okay. Perturbations in the gas. So we have seen yesterday the structure formation talk. So the biggest structures we expect from these processes are at these transition zones of the ionization. So you can imagine if you have a change in the accretion stress, you have a change in the surface density, and this, of course, gives then perturbations in the gas, but even more perturbations in the dust surface density, because these dust pebbles start to readily drift, start to concentrate in pressure maxima. And on top of that, at these regimes where you have this gas surface density bump, you can have Rossby wave instability, you can have vortex formation, and even further azimuthal dust concentration. Here an example how this looks like, a 3D non-ideal MHD model showing you a lot of physics included here. We couple here the dust opacity to dust sublimation. You see here the inner rim where it's so hot that dust is sublimated. We have the MRI operating. This is from Herbig star up to 0.8 AU. You see the dead zone edge here indicated by this rise in the surface density due to the lower stress, and then also a very efficient dust trap. Okay, so let's summarize for the MHD part. So if you have high enough ionization and a strong magnetization, actually the MRI and the magnetothermal driven winds do the job of your gas accretion. For the MRI, it's probably not so helpful for the dust growth. You can imagine it's very hot, and if there's dust, you have these strong turbulent velocities, but it could be still very interesting for the MRI in the outer part. So this is what we have to still investigate. For the non-ideal MHD layers, we think that these present only low turbulence level, and the gas accretion here is really cannot really help for the gas accretion, but it's good for the dust growth. Okay, let's focus now on these non-ideal regimes, because what I will now show you are the hydrodynamic instabilities which actually operate once the magnetic field are completely decoupled from the gas motion. So then the hydrodynamic instabilities come into play. But to understand those better, we have to understand this concept of the cooling time, so tau cool, which is here the cooling time, times the orbital frequency. You see on the y-axis, the different regimes, slow cooling when you are ever very optical sick, so this is optical sickness, or very optical thin. And actually the fastest cooling you expect exactly where the radiation can escape, so the tau 1 line. And this is obviously connected to the dust by the dust surface density and the dust opacity. So this is very important to remember, and especially for the smaller grains, so grains up to 10 micron, they provide to the optical depth, so they are really crucial for this cooling time, and as I will show you also then very important for the hydrodynamical instabilities. Okay. The thermohydrodynamic instabilities, so they can be here divided into these different cooling regimes. So where you have very slow cooling, very fast cooling, whereas this is only the primary requirements. The secondary are also listed here, whereas one can already here see that it's the vertical shear instability which has a requirement which is nearly almost met, right? The radial temperature gradient just comes out of a passive irradiated disk. Whereas for the other two, it's a bit more difficult. So the zombie vortex instability requires a nonlinear forcing, so it doesn't operate from itself. And the convective overstability needs very steep gradients, so probably appearing only at the edges of gaps. Let me quickly go through. So zombie vortex instability, it produces vortices. Here is vorticity. What is here important to mention, this operates only in the upper layer, so not at the midplane layer. And alpha values are probably still low. This has to be still investigated. Regimes of appearance, as I mentioned, is away from the midplane. So showing this plot, it is a gray zone. So for the convective overstability, alpha values are a bit higher, 10 to minus 3, produced by vortices which appear here. And again, this is operating where you have very, very steep gradients, ever in the density on the temperature. And these vortices could be important, of course, for dust concentration. And then the vertical shear instability, where we think it could operate in a large region in the disk. Alpha values between 10 to minus 4 to 10 to minus 3. And what is very characteristic are these large-scale vertical gas motions. gas. And it also produces vortices, and it's also important for the vertical dust mixing. So here, plot occurrence map over height and radius, and in this blue hatched region, you see this is where we would expect the VSI to operate. And this is very, very sensitive on the dust properties and on the gas mass. So if you have very massive disk, this can be larger, and if you have, let's say, a low mass disk or very, very large grains, this also shrinks. So it's very, very sensitive to this. So let me now show a movie from Liz Frowell's work. So it's a line integral convolution plot of the VSI in action. You see here, this is the midplane layer, upper layers are atmosphere, and you see these large-scale motions through the disk. So this is what's going on for the VSI. It really shakes up the whole disk structure. And in between these large-scale motions, you can have small vortices, meridional flows, which could also then concentrate locally grains. But from this, you already see it can be very, very efficient in mixing up or lifting up grains to the upper layers. Okay, so to summarize, so the thermohydrodynamic instabilities, they are probably not relevant for the gas accretion, but I think for the dust growth, they could be very, very important because they can concentrate locally grains even further. Okay, let's move on to this part of the dust. So probably, when you want to grow dust to planets, you have to go through many, many orders of magnitude in size, starting from these fluffy sub-micron dust grains to the dust pebbles, planetesimals, to the rocky planets. And for us modelers, actually what is very important is the coupling to the gas, which we express in the Stokes number, so which is here the stopping time of the grain times the orbital frequency. And you see here for very, very large Stokes numbers, the motion is decoupled, and for very, very small Stokes numbers, the motion is coupled. So in a sense, these small grains couple to the gas motion very efficiently, and that's why we, in scattered light observation, we actually see the structure, the gas structure, the 3D structure of the disk. But now the funny part happens, obviously, at the Stokes number 1, because here it's very, very dynamical. So the grains start to radially drift, to concentrate, so they react to the gas surface density extremely efficient. And therefore, they can also concentrate. And this parameter is important, the epsilon value, which is the dust density over the gas density, so the local concentration value. And if this value is above 1, then the dust density dominates. Okay, let's move on. So for planetesimal formation now, there are 2 pathways which we know from the past. So the classical one was just due to settling. You grow your grains, so the grains settle to this midplane layer. You see here very close to midplane. You get a high dust concentration, then you directly collapse into planetesimals. But this way is not so easy as we thought. So now recently, more and more people look at pressure maxima, because here, as I mentioned, the radial drift can concentrate the pebbles quite efficiently. And because we have these different instabilities, you naturally get these changes in the surface density, and you can concentrate your pebbles in this location. So this you really predict just from the changes in the stress to pressure ratio. Okay, there are other pathways. Also some works investigated the secular gravitational instability, which is here interplay between gravitational instability and the dust track force, also creating here rings and being able to generate planetesimals. What was a famous pathways now in the last 15 years is the streaming instability. So first you have to concentrate your grains at a certain level, and then the streaming instability kicks in, and then with a further strong clumping, you also can form planetesimals. So this is the part where I will focus on the streaming instability. So we know this now since a couple of years. These models were mainly done with single dust size. So you put all of your mass in a single dust size, and this allows you then to study the linear regime and the nonlinear regime. And in the nonlinear regime, what we saw sometimes is these strong clumping events. And these strong clumping events can then produce planetesimals. So you can imagine it's a bit like a pebble cloud, which then collapses into a planetesimal. So let me explain this in a bit more detail, this simulation here by Zhao Zhenyang. So these are different simulations showing a local box simulation of this dust and gas feedback. You see streaming instability in all three simulations. The streaming instability is operating, but only in the lower one where the solid, the total amount of solids is higher than usual. It's here indicated by the C value. Then you can see this strong clumping. So we have these pebble clouds, which could then eventually produce planetesimals. Okay, a lot of people investigated, where is this regime of strong clumping? You see that over the past, this regime extended, and we still think that this is not the end of the game. So it might be, that the resolution was not enough, or that the time scales are here connected. But this is something which we will investigate even further, so where this strong clumping can appear. So what was interesting, in the same time, a new, let's say, class of instabilities was discovered. They call it the resonant track instabilities, RDI. And they actually claim that the streaming instability is a subclass of this type of instabilities. But we have to be aware that it's only true for a certain parameter regime. For example, in this case, when the epsilon, so the concentration of dust is here smaller than 1 and the Stokes number is smaller than 1. But it might be relevant for the very, very early phases, so where you have the collapse. For example, there is a settling instability, so once these grains start to settle, they can already clump and hence or grow even further. What was also new was that for the first time we can now also have the streaming instability with a dust size distribution, which is obviously more realistic. And what the people here learned is that the instability has a bit more tight requirements, but some models also showed this strong clumping. But there are some caveats. So if you have external turbulence, it can damp the SI. And also what is here nice, there is a new class, which is here called the vertical shear streaming instability. So just by the fact that you have this pebble layer and the gas layer above, which have a different azimuthal velocity, you can get a new kind of instability. So this has to be investigated. Okay. So to summarize streaming instability, obviously the turbulence from the streaming instability is low, but it's very good for the dust concentration and to grow the dust further. Okay. So let's go to the streaming instability pathway to planetesimals. So a lot of models were then done studying the initial mass function. So from the size, we think that this works quite well. So we produce these 100-kilometer bodies. But actually from the IMF, it doesn't look too good when we compare actually with observational constraints in our own solar system. What was good was that inclination distribution and binary refraction is actually explained very well. So in this plot here, what was a model from David Nuswarny. But what was here important to mention is that this binary distribution and inclination distribution you also get from a pure gravitational collapse of a pebble layer. So this has to be a streaming instability. Okay, but here I also should look at the chapter 20 talk, which will here cover the planetesimal formation in much more detail. Okay, let me come now to the part where we want to observe actually this turbulence. In the last 10 years, people tried to observe the line broadening, and they mostly found very, very small turbulent velocities, which was a bit of a surprise for us. But then actually, when now these new ALMA observations came, so where they look at the 12CO emission layer, you probably know or understand why this line broadening is so small. If you look at this plot here, which shows here 3 different disks, height over radius, and you see here the 12CO emitting layer here in gray, what you notice is this emitting layer has a very narrow range. And when we speak about turbulence, we speak about the largest eddies, right? So eddies which actually cross or which has the size of a pressure scale height. So we were actually not so surprised that when you integrate not over many eddies, so you just see let's say the edge of the eddy, then you don't expect this line broadening. So you're probably only sensitive to these very, very small eddies which have a much smaller scale in the turbulence strength, and therefore this line broadening is so small. But there are other ways to probe the turbulence. So a very famous one was looking at edge-on disks. Here a paper by Marion Villeneuve. Here you see this beautiful, very thin, dusty disk layer. But you also, what is here important to mention, that they are probing here the Stokes number over alpha ratio, right? Because they don't know exactly the size, so they are sensitive to this ratio. But this is also what we have learned is that the turbulence has to be also low at the midplane, whereas what this line broadening is probing the upper layers. This measuring here this thickness is really probing the midplane layers. That's a nice way to understand or investigate the turbulence at different layers in different regimes of the disk. Okay. Also, what is a really new adventure is now with ALMA, you can specially resolve the largest turbulence eddies. As I show you here, a work by Marcelo Barraza, which combines a lot of details. So this is a model. So it's a 3D global vertical shear instability model. And then what Marcelo did is he put it in a line radiation transfer. He calculates the line, profile, the centroid maps, and then at each pixel you can then fit, sort of profile to the shape, and then subtract the best fit Keplerian model. And what you are left is the residual. And then you add the noise, you do a ALMA synthetic observation, and that is then what we see or what is left. And what you can see is actually that the VSI turbulent motions can be resolved with ALMA. So that was very impressive, that we enter now a regime where we not have to rely on turbulent broadening, which is unresolved, but we can actually go and look, how do the eddies look like, the turbulent motions. So that's really beautiful. You can see here the scales of up to 60 meters per second motions, so upward and downward motions are the ones which I have shown in the movie. And what was very nice is that this can be now observed. So this is by Richard Teague, a nice observation from MWC 480. And it's a similar method. So looking at the centroid map, subtracting the best fit Keplerian model at the surface, and then you are left with these perturbations. And what I was very surprised is that the scales look here very, very similar. Okay, but we will learn much more today at 4:10, so beware. Okay. Now to observe the wind is a bit more difficult. So there are here some models from Franz et al., and they look of the tiny dust grains which could be embedded in this wind. So this is here a scattered light model. You can see here it's difficult to see in this cone. You have some tiny grains which are entrained in the wind, and now the people start to investigate if they could actually see these tiny grains which are embedded in the wind. Another nice approach which I liked is here by Luca Ricci. He looks at the free emission. So this is a model, again, synthetic observation, now with NGVLA at 1 centimeter from TW Hydra. And in the top, you see that's a model from a photo-evaporation-driven wind, and this is a MHD model. And because the photo-evaporation-driven wind covers a much larger range, so where you ionize, where you have these high temperature layers, he sees this free emission much more extended. And with NGVLA, we would actually be able to specially resolve that and to then distinguish in this, for these two models. So that is a very nice idea, and hopefully NGVLA goes online soon. Okay, coming already to the summary. So really the take-home message here is that the MHD instabilities and the thermal winds, they are very, very important to explain the gas accretion. And what they really require is ionization level, a high ionization level, and a strong magnetization. So what you do is you carve out here the disk from the outer and the inner part and the upper part, whereas we still have a sort of layer where you can form your planets, where dust grains can settle, grow to planetesimals, and concentrate. So this is the big picture which we have since the PP6. For the perspectives, so from the theory side, as we have yesterday heard in the structures talk, we have really to advance in this coupled simulation. So we have, radiation transfer, non-ideal MHD, and also dust, because this is also what you should take home. These are all connected. The dust provides the opacity, it provides also the ionization, it captures free electrons. So this is all coupled, especially here this middle part here where we call it the dead zone. We have really to understand much more what is going on. What is also crucial is the magnetic flux transport. As I mentioned to you, when we have to go from class 0 to class 1 to class 2, there's still too much magnetic flux there. So we have to understand how we have to get rid of that. The dead zone edges, very, very important. So I think these are the regions, especially to form the first planets. So if people show embedded planets and they show these structures, then I always ask this question, well, how do you form your first planet? And obviously these changes in the accretion stress, they naturally give you these perturbations in the gas, and therefore they naturally allow the pebbles to concentrate. Yes, and then this, as I mentioned, the transition between the class 1 and class 2, this is not at all covered. I mean, this is an isolated disk, so what happens if you have a streamer, so if mass accretion falls onto the disk lately, these are all things which we can investigate in the future. From the observational parts, what we really need are magnetic field measurements, so Zeeman effect. So far, there was not so much done. Obviously, it's difficult, and I think we have really to understand. We even don't have a really proof how strong the fields are. So that would help us a lot in terms of the modeling, especially also to distinguish how strong is this MHD wind. Resolving the kinematic perturbation, I think that's a very, very big thing in the next coming years. So we will, I guess, learn a lot here from Alma. And also our hopes is to get some constraints on the surface density profile. So this is, this would be also a very, very big step, I think, in the future. Yes, and then finally, NGVLA would be a big game changer for this. Not only because you now can resolve, for the dust structures, for the detailed dust structures, probably these rings have substructures which we can resolve with NGVLA. So this will also be a big, important game changer for that. And with this, I thank you for your attention, and I'm happy to take questions. Thanks.
Thank you very much. I'm sure there are lots of questions. While I see people lining up, we have a request for Chapter 15 to please upload the talk to Mattermost. So that's the third talk of this morning. Please upload it to Mattermost. And with that, we'll get right to the questions. Please, state your name and where you're from, please.
Peter Voigtke from Graz, Austria. As an astrochemistry modeler of disks, I wanted to make you aware of the situation in the midplane concerning the charges. So yes, the electrons can disappear very, very effectively on the grain surface. So you actually charge up the grains negatively in the midplane, but there are still then positive molecular ions around. Now, let's assume this is correct. There would be two consequences. First of all, can you take into account these molecular ions when it comes to, making your alpha? And the second question is, when you have actually equally charged grains everywhere, would that affect these instabilities? Thank you.
Yes, very, very good point. So of course, I could not explain everything, but you're absolutely right. So we think that you have very, very lot of negatively charged grains. So what you have mentioned, it goes in the direction of the ampular diffusion, right, where you have to look at the ions and the electrons and neutrals actually separately. So far, the models are single fluid models, meaning that we have to make approximations about that. But you're right. I mean, these charges of the dust, they are extremely important, especially at these transition layers, right, where you have a change of the charges, right? You have positively charged grains where you have the UV, and then you have this sink of negatively charged grains. I think this is just starting. So first models appeared, and I think we have to look in that in much more detail in the future. I mean, you're right. Thanks.
In the middle? Yeah.
Hi, Andrei Zella from Rice University. Thank you, Mario, for the nice talk. I have a comment and a related question about the what you said about the fact that the low measured turbulence is due to the fact that CO only probes a small layer. I think in reality, the situation is more complicated because it's true that the line is optically thick and the peak of the line probe this small layer, but the wings of the line become optically thin and you can probe all the way down to the midplane and beyond. Indeed, we use CO to measure the temperature in the midplane. So I'm not sure I agree with the statement that the turbulence is low. The question is, did anybody do the painful exercise of simulating observation from models that have higher turbulence and then observing them and retrieving a measured turbulence and checking that, I mean, because if what you say is right, then you should recover a small turbulence from models that have high turbulence,
yes.
if that's the effect.
So we have done that. So it's actually in Marcello's paper, so it's hidden. I try to sell it. So he has really done it. From 3D line radiation transfer, we don't see any broadening. Even there is a turbulent structure on the upper layers. So I think it is true. But obviously, you're right. The wings are extremely important, right? I mean, this is something, I'm not sure we are there yet, right, from the signal to noise, but I think we will have much more results on the wings, right, in the future. But from the total shape, I think we have confirmed that in Marcello's work. So you should take a look. Yeah.
Thank you.
Thanks.
Excellent. Over here.
Hi, Francesco Lavascio from ENS Lyon. So, talked about a bit streaming instability with polydispersed dust, and I was one of the people on a few of the papers mentioned. And one of the really sort of less stated results is that the polydispersity of the dust changes one character of the streaming instability especially much, which is its relationship with turbulence. So while we say we have slightly more stringent requirements in general, if the disk is at all turbulent, it's sort of impossible to have any linear growth of the instability past alpha 10 to the minus 6. But this is really sort of thinking about turbulence in terms of alpha and the dust diffusion. Do you think that maybe it's time to move past this sort of like very basic model of turbulence and think about something better? And do you have an idea of what that could be?
Well, yeah, very good point. I mean, that's actually what, what I have here in the first part of the section. So when you have the 3D hydro instabilities here operating together with the streaming instability, then you should know, right, if it works or not. So we have to go in this direction, exactly as you say, But it's extremely difficult, right? You need these many dust grain sizes, and you need, on addition, this high resolution, right, to resolve the hydro instabilities. So it will be a challenge, but yeah, perhaps in the next 10 years we will progress. I hope we will progress there, but you're right. I mean, we have to do that. Yeah.
Thank you. Next question from over here.
Hi, I'm Dao Chongqing from NRL. Thank you for a great review. So I think so far the attempt of ARMA CN-Zeeman observation can only give an upper limit about 10 milligauss at a radius of 50 AU. I feel it's very kind of close to your value. What's your comment on this? Should we go for higher angular resolution observation?
Yes, very good point. So that's actually what you say is it's very important, right? What we know is probably we don't have these strong fields which we expect from collapse, right? But it's actually in the regime what we predict for our disks. But we have to go down to milligauss level to really be sure, right? Because if the magnetic field is now milligauss or 50 milligauss, it makes a big change, right, in the modeling. So this, I mean, it's the Zeeman effect, right, is sensitive to the strength of the field. So yeah, I think it would be really worth to go into longer, some observations to get down. Yeah.
So what's the structure of field in your model? Should we look for face-on disk or edge-on disk?
A good point. So the magnetic field structure is dominated by toroidal fields because of the upwinding effect, because of the Keplerian shear. So the toroidal field is the strongest, so this would be the way to go. So if you want to see something, choose your disk inclination so that it's sensitive to the toroidal magnetic field. Thanks.
Excellent. Thanks very much. At the back.
Thank you. Hi, Mario. So
Yeah.
I'm Hiroshi Kobayashi from Nagoya University. So I want to talk about the firstborn planetesimal size. So it can to compare with the solar system minor bodies, we need to consider the positional evolution of the planetesimal in protoplanetary disk. So,
Yes.
Okay, so.
Yeah, it's a good point. I mean, that goes in the direction what I wanted to mention, that the IMF is not fully consistent. You're absolutely right. They don't cover the full collisional evolution, right, in these simulations. So that's a good point.
I have a paper about the collisional evolution in the protoplanetary disk, and it can change the size of planetesimal after the planetesimal formation.
Very good. I see.
It strongly depends on the alpha value. This is
I see. Yeah.
This is my 2016 paper.
Thanks a lot. Yeah, that's a good point. I mean, that's obviously very important. So what I wanted to mention is only the initial stage right after the formation of the planetesimals. Yeah, good point.
Thank you.
Thank you. I'd like to take the chair's prerogative here and just ask a question. You mentioned that at the edge of the MRI zones, you can get instabilities that will lead to pressure bumps, and then you sort of talked about perhaps dust trapping. And I was wondering whether you think that will lead to ring-like dust trapping, or whether it will lead to clumping dust trapping, or whether or not it's really stable enough to keep dust around.
Yes, that's a good question. So, of course, in first order, we see rings, right? And these perturbations produce rings. And if the bump is strong enough and you generate a Rossby wave instability, this ring will break, and you should see a concentration of dust. I mean, this is not seen with ALMA yet. We hope that going to NGVLA, probably we would see that, but this is obviously something we have to look further in. Yeah, it's a good point.
Perfect. Thank you. Yes.
Okay, Takeru Suzuki from the University of Tokyo. My question is regarding clumping of dust particles by streaming instability. You explained that some recent theoretical works show that a small dust-to-gas ratio is sufficient to trigger clumping, which is in contrast to the classical understanding that some relatively higher dust-to-gas ratio is necessary. What makes that difference?
Yes, that's a very good point. So you're right. I mean, there's some works which show that this strong clumping starts already for an epsilon value above 0.3 in the midplane. So this is under investigation. What I can say is it's highly nonlinear. And sometimes it happens, sometimes not. Even I did some simulations, and this is still something we have to understand. So it's really difficult to predict this clumping, right, in this sense. But what we see is, if you, for example, change the scheme or the resolution, then it has an effect on this parameter regime. So therefore, I think we have to go much more in these boundaries, right, and see if this strong clumping appears. Yeah.
Okay, thank you. Still under investigation.
Yes, absolutely. Thanks.
Excellent. We have time for a few more questions. Over here.
Yes, Tristan Guillaume, Observatoire de la Côte d'Azur. I wanted to ask you, in your view, what happens with viscous heating and the temperature of disks with this kind of new developments?
Yes, that's actually a very good point. So what I haven't mentioned is that the hydro instabilities, they are not really efficient in producing heat, right? So, but here it's the regime where you have most of the optical depth, right? Where you would actually produce this heating event. So eventually, at the beginning we thought, well, the MRI can do the job, but here you don't have dust grains, right? So what we think is that, well, there is a small overlap. I mean, I have showed it in one of the plot of the global models, so where you can have, MRI accretion heating trapped, and you can heat, but then we would expect bursts. I mean, it goes in the direction what Agnes Koschbel showed yesterday. We should see variations in the accretion. But for a long time, the temperature structure should look similar as a passive irradiated disk. So for now, yeah, we don't see a region which should show this accretion heating right right there. I mean, this is a very good point you mentioned. So, because if you look at this picture, it tells you right there, where you have most of the dust, right? You don't have a strong turbulence. You don't expect to have a strong accretion heating. So this has to be investigated. But I think it goes in the direction that it is probably variable accretion at the beginning, and then the disk turns into a sort of passive irradiated disk. Yeah.
Thank you.
Thanks.
So thank you for the question. Mario, you've done something either really right or really wrong. We have Inetsuka-san up at the microphone, so take it away, Inetsuka-san.
Shuichiro Inetsuka from Nagoya University. Okay, by the way, very nice talk and very comprehensive. I'm impressed. So you may guess my question. Okay, now streaming instability has difficulty with grain size distribution, so its condition is very severe. But under that condition, secular gravitational instability may operate. Okay, and typical criticism to the secular gravitational analysis is a lack of the consideration of effect of vertical structure, but that is written in the chapter. However, now, last month, a new paper, article is on the archive, and it's by Tominaga et al., and who studied the effect of a vertical structure. And the actual result is that under even with stratification, dust sedimation and large-scale height of gas, actually growth rate of the secular gravitational, it does not change so much.
Okay.
So, nice. So then I think that would be the one of the most promising mechanisms to create planetesimal. And in addition to that, that will automatically create multiple rings,
yes,
even at the, say, 100 AU position. Can you comment on this?
Well, I mean, it's nice, right? I mean, what I think is we have to do more work, right? And because it's very difficult, right, to investigate all these dust tracks, self-gravity in a global 3D model. I think, I think that is probably what takes still people, away from studying all these regimes. But you're right. I mean, probably this is the way, right? I mean, the more we learn, right, from the SI, it becomes a bit more difficult. I totally agree to you. So, but we should be open to different regimes. So.
And actually, I like to encourage other people, other group also work on this SGI.
Yep.
Yes.
Yeah. Okay.
Thank you.
Thanks. Yeah.
Thank you. We have time for 2 quick questions.
Okay. This is maybe even a comment. Mordecai Maclow, American Museum of Natural History. So just to give us some hope on polydispersed streaming instability, way back more than 10 years ago, Johansen et al., 2007, we showed that a 4-bin polydispersed, so a bit polydispersed, interacts constructively with MRI turbulence. This turbulence concentrates as well as diffuses. Alpha turbulence only diffuses. So looking at polydispersed SI in real turbulence will be of great interest, I think.
Yes. No, it's a good point. I just wanted to make it clear, right? Where you have the MRI, you probably don't have the large pebbles. So this is the main drawback I have to say to this. But you're right. I mean, if you have, then you're right. Then it helps. It can help. Yeah.
It doesn't have to be MRI. It just has to be turbulence that can concentrate as well as diffuse. And I think we saw in your VSI models, for example, that there were regions that looked like they were probably going to concentrate.
You're right. For the VSI, the picture looks different. So here, as you say, you can have the pebbles and the VSI. So this is really a very interesting regime we have to look into the future. Absolutely. Thanks.
Last question in real quick.
Thank you. So I'm Yusuke Tsukamoto from Kaohsiung University. So I'd like to ask this perspective. So is there any simulation study that the Fitch includes dust growth and no ideal MHD simultaneously? Because the dust growth changes resistivity and position of the dead zone, etc., etc. So is there any high-resolution simulation which includes such a dust growth and a change in the resistivity?
Yeah, so that's a good point. So many groups want to achieve that. So we are working on that. So what I can recommend is Timothy Large paper. So he has a simplified sort of alpha model which couples exactly what you said, the non-ideal terms with the dust growth. And we see it matters, as you say. So you should take a look at it. It's in the chapter, so it's there.
Okay, thank you.
Thanks.
Excellent. I'd like to thank all the people for asking questions and thank the speaker once more.